Well, we've done the Earth and its magnetic field, we've done stars, we've done galaxies, and we're now going to have a little bit of history from Professor Peter Coles from Maynooth on lights all askew in the heavens, the 1919 Eclipse expedition. Peter.
Thank you. Thank you. I didn't choose the title myself. It's rather too poetic language for me. It's actually a headline from the newspaper in 1919. And what I want to do here is to just give a brief overview of one of the most famous experiments and measurements in the history of science. In fact, about 20 years ago, I took part in one program in a television series called 6 Experiments That Changed the World. And the number 6 was this one. And I think that's not an exaggeration. It didn't actually change, it didn't move the Earth itself, of course, but it certainly did change the way we see the world. And it replaced sort of Newton's conception of gravity and mechanics with Einstein's. I'll say more about that as we go along, but first of all, let me explain why we're doing this today. The measurements that I'm going to talk about took place in an eclipse on the 29th of May 1919. Now, it would have been nice to been able to mark the centenary at one of these meetings, but of course the May meeting is the AGM, and we don't have these kind of talks at the AGM. So this is the nearest one we could manage. And of course the other thing is that when it was deemed that it was a good idea to have a talk about these famous measurements, only one name came to mind. But unfortunately, Richard Ellis couldn't make it today, so you've got me. Right, so what I'm going to do is to just... incidentally, for those of you who don't know where Maynooth is, that's what it looks like. It's in Ireland. It's about 25 kilometres from Dublin. And that's not my house, by the way. That's St Patrick's house, part of the old part of the college. So we all know what a total eclipse of the sun is. It's a thing that looks like that. You have lots of science can be done when the sun's blotted out. The sun basically gets in. A lot of people are interested in solar physics, of course, but for many other astronomers it's a nuisance, and it's kind of nice when something gets in the way and blocks it out, which it happens during an eclipse. And this one is actually a rather nice one that shows you the corona, which you can't usually see in daytime anyway. But the relevance of this was the crucial measurements that were done 100 years ago, that basically it was a perfect measurement, a perfect kind of experiment, basically, because there were 2 clear predictions on the table at the time as to what would happen. One emanating from Newton's theory of gravity and one emanating from Einstein's then new theory of gravity. I haven't got time to do all the theory here, but there's a picture of Newton. And essential part of Newton's theory, this is a translation of a quote from the Principia, the general scholium of the Principia, his magnum opus, saying what Newton actually thought about space and time. And you see what he says about it is almost religious. Well, it is very religious, in fact. Because the supreme God is a being eternal, infinite, absolutely perfect, he endures forever and is everywhere present, and by existing always and everywhere, he constitutes duration and space. So you cannot get more absolute than that. Space and time in Newton's concept are manifestations of a divine presence in a real sense. What happens with Newton's theory is that, well, we've all done Newton's theory as undergraduates, and even at school, that you have basically laws of motion and you have a law of gravity. One particular force law is the law of gravity. And there's a curiosity in that, which is that mass appears in the Newton's laws of motion, in the sense that F equals ma. M in the F equals ma represents the resistance of a body to being accelerated. It's its inertial mass. In Newton's gravitational law, you also have 2 masses. You have the mass that describes how a body exerts a gravitational field, and then you have another mass which describes how a body responds to a gravitational field. So F is g, m1, m2. Now, you take it for granted when you do Newtonian calculations that all of those masses are the same thing. And it's not obvious at all that that has to be the case. And one of the things that inspired Einstein, there's a picture of Einstein, looking rather clever, as he tended to do. One of the things that motivated Einstein was that to try and get to the meaning of why is it that these different masses are the same. And maybe there's some kind of equivalence of all of these masses. Maybe there was a principle behind it, the equivalence principle. So there's just a little bit about Einstein. Everyone knows most of these things. He was born in 1879. He wasn't a great success at school. He dropped out of school. Needed 2 goes to get in past the entrance exam. When he finished his degree, he was generally perceived, the phrase was too lazy and too disorganized to become a professor. The idea of someone being too disorganized to be a professor is completely beyond me. But he left, of course, famously to become a patent clerk, where he worked in a place where there was an excellent library and he had plenty of time to do interesting things. And of course, 1905 was his year of miracles, where he produced 3 amazing papers, including the special theory of relativity, E equals mc squared and all that. People often think, in fact, there was a big celebration of 2005, the centenary of the year of miracles. People think that 1905 was the thing that made Einstein famous. Actually, it wasn't. It was 1919 that made him famous, and I'll give you evidence for that later. It took almost a decade for him to get on to his general theory of relativity. He presented it in 1915, and papers were circulated in the following year. So in the various concepts in this, was one of the reasons why I like this experiment, the Eclipse experiments particularly, is that they allow you to sort of describe some of the effects of general relativity and why they're different from Newtonian theory in a fairly simple way. And the other thing I like about it is that I spend most of my time doing statistical things in a cosmological setting, and the analysis of the data from these eclipse things is a very nice case study in how to do, and in fact in some cases how not to do, a statistical analysis of experimental results. So I'll just touch on a couple of those things here. So one of the things that emerges from general relativity is space is no longer an absolute thing. It doesn't exist, space and time don't exist apart from material bodies and their motions. They actually respond to that and influence it. So space, in particular, space curves, and light traveling through space gets bent as a result. So rather than being a sort of absolute passive stage on which particles and bodies move and interact with each other, it's actually part of the action. Space is flexing and warping and doing all kinds of things. So light, in the absence of a gravitational field, basically light travels in a straight line through a flat space like this. This would be Minkowski space. You've seen all of these. On the television program that I was talking about, we tried doing this with a big, massive. It was actually a concrete ball that we nicked from the top of somebody's gate post. We put it back, so it's all right, and a large trampoline, and we put the ball inside in the trampoline and tried to get a golf ball to go around. It's actually really hard to make it do that properly. It's the analogy that works in your head, but actually in practice doesn't work particularly well. So the idea is if you put a gravitating body in here, the trampoline gets curved, and a light particle traveling past it no longer goes in a straight line but gets twisted, deflected past it. So this is the idea behind the eclipse measurement. And this is what you'd see. This is not to scale. I know some physicists who think that they are. This might be to scale, but there we are. So the idea is that you have the sun in the way, but it's blotted out during an eclipse. Obviously, you can't do this unless the sun's light is extinguished. So you basically imagine that you had a star that's actually in this position in the sky when the sun is not there. the light gets a deflection as it passes around the star. And what you see on the Earth, we'll actually use a telescope probably, is the direction that the light ray enters your eye or the telescope. So you extrapolate the position back along that line. So what appears to happen when you put the sun in the way is that stars appear to move away from the sun, radially outwards. So this is actually a really interesting story because in Newton's Optics, which unlike the Principia was actually published first in English in 1704, he wrote this rhetorical question. Newton wrote this question: do not bodies act upon light at a distance and by their action bend its rays? So that really sounds to me like he kind of thought this was going to happen with light. There's no evidence that has come to light of any calculation of Newton's that actually does this. It took 100 years before von Soldner actually did the calculation. Basically, he assumed you have Newton's law of gravity, and light is a light particle, low mass particle, and it gets deflected. That's a calculation. It's quite easy to do. It's just a ballistic scattering problem. Very fast-moving particle deflected by the sun. And the answer is not much. Light from a distant star is deflected by 0.87 seconds of an arc if it's just grazing the solar limb. And it falls off with distance away from that. So it's less than that if you go further out. Obviously, you wouldn't be able to see this right grazing. But remember that figure. That's a kind of normalizing figure. For those of you who don't know the numbers here, 1 second of arc is the width of a human hair from a distance of 10 meters. Right? So that's quite a difficult measurement. So, and it's even more difficult for reasons which I'll show you in a moment. Now, actually, Einstein with it, so that's called the Newtonian value, 0.87 for grazing incidence. In fact, Einstein in 1907 started thinking about this, but he seems to have thought that this was far too small to ever be measured, so he might as well not bother with it. After talking to some astronomers who assured him that actually you can measure things that small in astronomy, he tried again in 1911, and there's a paper by him where he basically just says, well, if we believe E equals mc squared, then basically light has a mass associated with it because it has energy. They're massless particles making up light, but because there's energy, it should act as if there is mass. And he got the same answer, not surprisingly, because it's effectively the same calculation. So he got the Newtonian value in 1911. Later, after he worked out the full theory of general relativity, he did this calculation again, and he got that an answer which is precisely double the Newtonian figure. So people often ask, where does the factor of 2 come? Oh, I forgot this one. This is just a graph to show you how accurate positional measurements could be. Even back, 0.1 of an arc second, we've gone back 200 years. So it's feasible to make very precise measurements with astrographic telescopes. The difficulty is that these are proper observatories, very sensitively calibrated instruments. To do an eclipse measurement, you generally have to go in a field somewhere with portable kit, so it's much, much harder. But nevertheless, you could. It is possible to make very accurate measurements, sub-arc second measurements with optical telescopes. So where does the factor of 2 come from? Well, I was warned that I shouldn't put any maths in here, so if you don't like maths, look away now. The factor of 2 is quite simple to understand. Well, there's a mathematical way, which is that actually, if you do what Einstein first did, you actually only use the time part of the metric. That's the geometry of space. It only includes the time component. So, and that's the bit in Einstein's field equations that corresponds to the energy part of the energy momentum tensor. That's the right-hand side of Einstein's equation. So that's what he used in the first paper in 1911. This is what happens if you use the full theory. And you'll see this is actually the space part of the metric. And this factor here is the same as this factor here for spherical geometry. So what is actually happening here is that you get the Newtonian deflection of light but the light is deflected through a space that is itself curved. And that curvature of space is exactly the same effect, the same size of effect as the Newtonian thing, but adds to it. So you get double the effect. So another way of saying that, so if you didn't like that in terms of the mathematics, just think about it in terms of words. The key thing about general relativity is that not only does energy gravitate, or mass, so does momentum. This part corresponds to the momentum part of the energy momentum tensor. Okay, so the factor of 2 is basically because there's an additional effect of spatial curvature in Einstein's theory, which is not there in Newtonian physics. So meanwhile, there's a character called Eddington. There's a little potted history of him. He was actually made Plumian professor when he was only 30 or so. And he actually he'd been involved in Eclipse expeditions in 1912, but didn't get any data because it was raining in Argentina. In 1916, although there was a war on, information came across via De Sitter in Holland about Einstein's theory, and conversations began about the possibility of actually doing this test, because previously, before 1915, there was only the Newtonian value that anyone thought about measuring. Now there was a really clear test of a theory with 2 possible measurements, 2 possible values. And it was Dyson, the Astronomer Royal, in 1917, who realized that the 1919 eclipse would be perfect. Why is it perfect? Well, here's a nice picture of, that's Eddington and that's Einstein, obviously. Why was it so good? Well, the main thing is that in order to do this experiment, you need quite a lot of bright stars close to the sun during the eclipse, so you can actually measure the deflections. And during totality, incidentally, 29th of May 1919 is in the astrological house of Gemini. So naturally, during that time, the sun is in Taurus, and that's another reason why astrology doesn't work. But it's not only in Taurus, but it's sitting right in front of the Hyades cluster, which is a nearby cluster of very bright stars. So you don't just get 1 or 2 stars you can measure. In principle, there's a whole field full of stars that you can measure deflections. So that's the path of totality. 1919, there's another one that actually gave better results a few years later. But it went across the Atlantic from northern Brazil, from Sobral to Principe, which is an island in the Gulf of Guinea, what was off the coast of what was then called Spanish Guinea. The problem was, Eddington was a Quaker. Now, there's a mistake there. Conscription actually started in 1916, not 1917. Sorry about the typo. And Eddington made it quite clear that he would not be conscripted. He was a conscientious objector, and he potentially was going to be in quite a lot of trouble. Dyson intervened and basically got Eddington out of the draft on condition that that Eddington would lead the expedition if the war had finished by 1919. As it happened, the armistice was signed in November 1918, and that gave just enough time to prepare an expedition. There was actually quite a considerable shortage of labour because a lot of technical staff had been conscripted by this time, so it's quite a rush to get everything done. So there was a huge scale experiment requiring a massive research grant, £100 for equipment, and £1,000 for travel and labour costs. That's to move 2 pieces of kit, one to Sobral and one to Principe. The 2 main telescopes were taken from Oxford. Actually, Eddington went to Principe and Andrew Crommelin led the expedition to Sobral, 2 simultaneous ones. Fine. The 2 object glasses were ripped out of the astrographic telescopes and stopped down basically to reduce aberration. And a 4-inch telescope was taken to Sobral as a backup. Eddington chose Principe because the weather forecast was better in May 1929. It was a bad decision. And these 2 object glasses there. Now, that's a picture of the Sobral setup. So you'll see here that's the 4-inch, and it's square tube, and that's the astrographic telescope. These astrographs are about they were standard kit around the early part of the 20th century, made by Howard Grubb in Dublin. 13-inch refracting telescopes with a very long focal length. And you'll see these little mirrors in the front there, coelostats. So the telescopes are roughly horizontal, and they reflect the light from the eclipse into the telescope. So that's how it works. Where are they now? So I mentioned this. My Irish colleagues would not forgive me if I hadn't mentioned this. These telescopes, the astrographics, still exist. The Oxford astrographic was given to Keele University in 1962, and as far as I know, it's still there as a teaching telescope. And I think the RGO one moved to Herstmannsson is actually still in Herstmannsson. You can look at it, but it's not a research telescope anymore. The 4-inch telescope and the coelostat are on display at Dunsink Observatory just outside Dublin. And in fact, they're not, because of the centenary celebrations, they're currently on their way to Sobral, where they'll be on display there to commemorate the centenary. So that's the famous 4-inch object lens, and that's the coelostat. It's actually you've seen it, it's not a lightweight piece of kit at all, it's quite a clunky object. Anyway, yeah, that's the little picture I showed you before. This is the setup, and then this is actually from a serious scientific publication called the London Illustrated News, which is quite a nice graphic, actually. And there's the path of totality again. So what happens, I'll just show you. There's 4 stars. This is not actual data. I've used my skill at computer graphics to put the sun in the middle. And with the sun there, what happens is that they all move out a little bit. And so you see, that's in principle, you see the positions shifted radially outwards. That's the idea. Now look at the actual plates. This is a 1919 plate from Sobral. And you see there's the eclipsed, there's the rather wonderful corona, and there's the 2 clearly visible, very bright stars. So it's actually quite hard to see the stars on the plate, never mind measure the positions. And worst of all, the Sobral astrographic had a lot of optical problems. It was blurred, it went in and out of focus, and there was some confusion about aberration. That is a star image from one of the Sobral plates. That's 5 arc seconds across. And that is the calculated deflection, the little red arrow there. So you've got to centroid those things and measure the differences. It's not easy. So this is what I'm going to run out of time here, but let me just show you. There are several things that could produce a deflection other than the Einstein, whether it's gravitational deflection or not. So these are measured. So what you do is you take a comparison plate with the sun somewhere else in the sky. You take the eclipse plate with the sun in the you basically measure the difference between the positions of the stars on 2 plates, a difference measurement. So there are other things other than the deflection, the gravitational deflection, which is this term. There's a centering error, and there's a scale difference between the 2 plates, and there's a twisting difference between the 2 plates. What you have to do is measure all of these things simultaneously and try and take out the non-gravitational part. You need several measurements to do this. 1 or 2 star positions will not do it because it doesn't solve this. There's more unknowns than there are positions. So it's tough. So Eddington went to Principe, Crommelin went to Sobral. It was cloudy in Principe. In fact, it chucked it down with rain. There was a tropical thunderstorm before the eclipse. Crommelin had better weather. And the short version of the story is that Einstein won. Let me just show you what the original results were. Principe actually only had 2 very low quality plates, and Eddington did something rather strange with the data, but managed to produce an answer. So remember, this is 1.74 for Einstein and 0.87 for Newton, this number alpha, which is the grazing incidence number. 1.62 plus 0.45, plus or minus 0.45. Now that number he got without technically having enough measurements to determine that solution. He played around with it, and that was his best. The main Sobral astrographic, the proper telescope, gave a result bang on the Newtonian value with a large error. And this was because of optical problems with the telescope. The 4-inch backup telescope, the little one, was the star of the show, as it turned out. It gave a high value consistent with Einstein's value. Now, people have been, said a lot of things about the data analysis. What I will say here is that all of the measurements are actually published in the Philosophical Transactions paper in 1920, and you can reanalyze this data yourself if you want to. I've been running an undergraduate project for many years where I get the students to take the data and actually figure out what's the right answer. And actually, I don't think Eddington did anything particularly wrong with this. He was, there's an old military saying that no plan of battle ever survives first contact with the enemy, and I think he had to improvise. Anyway, in 1979, the Sobral astrographic plates were remeasured using an automatic machine, not by eyeball, but by an automatic machine. And they actually they corrected some of the errors that Crommelin had made, and it's actually much closer to the Einstein value. So this can be discounted, really. Great tragedy of this is that none of the plates exist or can be found. I won't go into the story of that. It's fascinating in itself. Here's the eclipse from 1922. Which actually had many, many more measured deflections and gave a very clear measurement. Now, I'm running over time, but in 1919, when the results were announced in November 1919, after a lot of work to reduce the data, there was a joint meeting of the RAS and the Royal Society, and it made headlines all around the world. It was really phenomenal. And there are lots of interesting aspects of that. One was because it was the end of the First World War, and I think people were sick of all the terrible stories about international conflict that had been going on. But if you read the New York Times annual index of proper names, every year they basically list everyone who's mentioned in the New York Times. There is no mention of Albert Einstein in that annual index until 1919. And after 1919, there is no year without a mention of Einstein. So there was a phase transition there with Einstein. I always wonder what would have happened had the expeditions in 1912 and 1914 gone ahead, because remember, Einstein had a paper out with the wrong value on it. So that's an interesting speculation. So I couldn't end without mentioning this, of course, research on relativity. So basically, Einstein was right. In the long run, these experiments have been repeated over and over and over, and but they always produce the Einstein value. This is the thing that you can't have missed this week. There's hardly been a newspaper without it. What I'll mention here, which I told my Irish colleagues, is that this is 42 micro arc seconds across, this image. So that's the equivalent of a human hair placed in Dublin and viewed from Cork. Of course, you wouldn't be able to see it because there'd be people in buildings and things in the way. But that's not the point. So I'll finish there. Thank you.
Well, sadly, I think we've run over time, Peter, and we won't take any questions. But that was a fascinating piece of history, and I'm sure it's a pity we couldn't have had this on the May meeting, but nonetheless, you've done us proud.